All right. So what are we doing today? We are on the final stretch, as I said. It's the last bit of the algebra textbook, and it is what they call system of equations. And the nice thing is that, you know what? You probably already know this already. You've seen it before in one shape or form. And the straightforward approach or takeaway for this, excuse me, is that this is basically when you're working with two or more equations. For all intensive purposes for this class, I can already tell you right now, for the textbook, as well as the homework, as well as the final, the most you're going to see is two equations. So there won't be any more than two equations. It's just fair to say out loud, oh, well, system of equations means when you have two or more. That's what makes it a system, right? Instead of every example that we've done so far, yes, you may have noticed that, oh, well, we've had multiple equations and multiple linear lines and multiple examples, and that's absolutely true. At the end of the day, though, it was only one line at a time, right? There was never a time where you saw, I guess, how should I say, multiple lines on a graph unless I pointed it out to you as an example or whatever the case might be, okay? So let me write that down, actually. We are working we are working with two or more, but remember for this class, it's just two maximum equations and solution. But what do I mean by solution, right? Well, we're going to go over several things, and I'm going to prematurely give you a breakdown of what they are. And at the same time, I will readdress them when we cross those paths today, as well as come next Monday when we're finishing up the topic. So what does that mean? So here we're going to do three things essentially. We're going to put it. Yeah, I like this. So we're going to first worry about methods of solving systems. And what happens is that within that, we have three of those methods. There's graphing, which we're going to go over today. There's substitution, which we will touch on today because I was able to get it to it in the other class. And then we have something called elimination. That's what I called it, or that's what I was taught. Elimination. When I was taking algebra for the first time, but some people have updated to call it the addition method because that's what you're essentially doing, you're adding. So the methods of solving systems, there'll be three kinds, these three. And what happens is that from those three methods, here's the second thing we're going to talk about. We're going to talk about what possible solutions exist. And what are those solutions? Well, there can be one unique. I know what everyone knows what unique means. It means one of a kind, right? You can't be very unique. If you're already unique, you are one of a kind. There's nothing else like you. But in mathematical terms, or mathematically, when you hear, oh, unique solution, not only is there a solution, aka answer, that is the only solution, right? There is no other solution. So uniqueness also has that exclusivity where you state, hey, there can be no other solution. This is the only solution. We're going to see what it looks like to have infinitely many solutions. Infinitely. Wait, did I spell it right? Infinitely. Yeah, infinitely. Many solutions. And then the third kind is, we'll see what it looks like to have no solution. So that means that you don't have an answer. You do have an answer. The answer is no solution. And I'll show you what it looks like. And then last but not least, the third aspect of systems is that we'll be systems involving inequalities. So if you notice the last couple of lectures, we were talking about a lot of graphing of the inequalities. That's basically just graphing and shading. So now instead of worrying about one graph at a time to do that, we're going to worry about two graphs with the whole graphing and shading. All right. Cool. So what do we do, or where do we go from here? Well, we're going to do the graphing first. All right. So if you haven't had this all written down, I'm going to give you another 30 seconds. Just make sure that it's all written down in some shape or form, so that, because you'll see me reference it by scrolling back to it often and say, hey, remember this, remember that, and then so on and so forth. All right, everyone have this written down, hopefully. All right, so let's start with that graphing, like I said. So we're going to do graphing first. So then they'll give you something like this, example 1, and they'll say solve via graphing. Like, it'll be very clear in the instructions, and they'll always give you a curly brace. Actually, I'll write it up here. And then they'll give you the two equations, and then you go from there. Now, that's the nice thing about a multiple choice exam, right? As I already told you, this final of yours will be multiple choice and be cumulative. And the thing though is that with the multiple choice exam, you can't graph, right? You can only pick graphs. So you have to be able to depict a graph. You got to pick the graph that's correct and go from there. So even though I'm showing you this, you might think, oh, right, well, you actually don't need this because we're not going to actually be physically graphing. Well, yes and no. If you are graphing quick enough, you'll be able to find answers faster than you would be able to if you are calculating. Not all the time, but sometimes. And then the other thing to keep in mind is that sometimes knowing the way the graph behaves or structured or whatever you want to call it, it will actually excel in terms of understanding its properties, movements, and all those things. So just keep that in mind. The hint here is that when you're solving with graphing, is that I'm going to tell you right now already that a unique solution is when the two lines cross at one point. So basically an intersection, that's what you're looking at. So whenever you graph and they cross as you expect it to, you go, oh, right, that is a unique solution. They cross at one point and one point only, and that's my answer, and that's pretty much it. Okay. So what do you do here? Now the graphing, I'm going to move quicker because everyone should be familiar with graphing at this point, right? So in purple here, I'm going to subtract the 2x so that we have it in y equals mx plus b, or slope-intercept form. So this is y equals, what is this, negative 2x plus 7. And then here in green, right, what I did was I'm going to subtract x on both sides again, but I'm going to move it down here and go negative 2y equals negative x plus 6, but we have to also get rid of that negative 2. So you do that by dividing, right? Divide by negative 2. And then this implies our graph is now y equals positive 1/2 x and then minus 3, right? So let's graph this really quick. Excuse me. And another problem, as you can imagine, with doing something like this is that obviously I'm going to do my best to graph this as accurate as possible, but it can get really choppy fast. So I just ask for your patience as I do my best to graph with it the greatest accuracy possible. All right, cool. So the purple one right here, I mean, I would love to do it in a different color as I normally would, but I can't because I got to keep the colors the same. So you have that positive 7, right? So you're going to go up 7 on the y-axis. So you're going 1, 2, 3, 4, 5, 6, 7 right here. And then the slope is a negative 2, but that really means m is negative 2 over 1. And remember, it's rise over run. So we rise how much again? From this point of 7, or 0, 7.
Down 2.
So if you, or anyone for that matter, remembers it the way they were taught from high school, down 2, then to the one right, that's fine, because either way it's going to work. However, the way I'm teaching, if you have seen from the videos and a couple of times I've talked about it, is that we always go up. We rise because just remember bread rising. If you bake, it rises. And then you run to the left or right based on the denominator, whether it's positive or negative. So the way I've been teaching it is that I go, you rise 2, but then you run to the left 1 because it's negative, because of that -2 right there. However, whoever that was that answered, thank you. If you go down 2 and then to the right 1, it will give you the same answer. So let me just graph this really quick. So like I said before, and I said many times when I'm teaching, if you remember the way you were taught and you're solid on it, by all means, you don't have to conform to my way. Do it your way, make sure it's consistent, you're good to go. However, if you are having trouble remembering how to graph, remember it's just always rise over run, right? Always go up, and then you rise, whether it's to the right or to the left, depending on whether the slope is negative or positive. But yes, that's good. So good. And then I'll do the same thing here as well for the green one, and I'll just move a little bit quicker. So here, in this case, you are going to start at -3. I'm going to go down 3, 1, 2, 3. The slope here, right, is m equals 1/2. So I would say rise 1, and then you move to the right 2 because it's positive. So rise 1 there. And then what will happen is, like I wrote that, rise 1, and then you go 1, 2. There's your point, and then you draw. I think I drew this rather accurately. Oh no, just a little bit more. There we go. Yep, I drew this one better. So if you graph this, and you know these points are 0, -3, and you know this one is 2, comma, what is that? -2. And then we got, in the purple one, we got 0, 7, and then this one we went up to the left 1, so that's what, -1, 9, right? If I zoom in, what does this point look like right here? You want to take a guess? Yeah, it's 4, -1. It's actually pretty darn close to it because the last class when I did it, it was a little bit off, but this one I did it a little bit better. So yeah, it's definitely 4, -1. And that'd be your answer. It'd be just 4, -1. However, you may see it in multiple representations. So if you're doing multiple choice, they'll definitely show it to you like this in coordinate form, 4, -1. Or they might even go as far as telling you x equals 4, y equals -1. So either of those are correct, but I want you to be aware of seeing either, right? And that's pretty much it, right? This, you can see that this is one solution. It's a unique solution. It crosses at a single point. It's an intersection. And yeah, and then that's pretty much it. And then that's their point of intersection, if you will. What questions here? Should be straightforward. All right, let's do another one really quick. So I'll move faster on this second one right now too. So here's example 2. I'll leave a picture up there for those that are still copying it. I'm going to give you the point. I'm going to give you a combination of, we're still going to graph, and your two equations are x minus 3y equals a -3, and then x plus y equals, what is that? 5 right there. then you do the same thing, right? So purple here, you can see again, I'm subtracting a negative x on both sides, so we're left with negative 3y equals negative x minus 3. But then when you divide each term by negative 3, we actually get y equals a positive 1/3 x and then plus 1. And you do the same thing here. For the bottom one here, you're going to subtract x again. And this one's nice because it's already done for you, if you will. You got, after you move the x, you just got y equals, what is that, negative x plus 5. And then you just draw your graph. Scroll up here now. Let's see how big this graph is. It's going to cross. Okay, yeah, I got it now. So this one, when I did it last time, the graph was a little bit wonky because I wasn't accurate enough. So hopefully this time around, I'll be able to get it right. I think we're going to the negative side too much. All right, cool. So what's happening here? Again, in purple, you have a positive 1. And you got a slope of m equals 1/3. So I start at 1. I'm going to go up 1. And we'll go to the right 3. So it should be right here. It should be this line right there. In green, however, I'm going to start at positive 5 for my y-intercept. 1, 2, 3, 4, 5. So that's right there. And then here you can see the slope. It's different, right? Remember, negative, invisible 1. So it's negative 1/1. So again, if you went down 1 to the right 1, that's fine. But the way, again, I show students when they are iffy on their graphing, you go up 1 because you rise 1, and then you're going to go to the left 1 because it is a negative. So your graph is right there. Let me draw this down. Hopefully it'll cross at the right point this time. It looks like it does. No, I still messed it up. It's supposed to be like right there. It's because I drew the little circle off a little bit. So it's actually supposed to cross right at that point right there, which is actually 3, 2. So this is 3, 2 in coordinate form, or again, of course, x equals 3, 2, 3, and then y equals 2. So if you got that, and you're like, hey, I can follow along, I know the intersection, it's good, then you're good to go. Because the graphing, again, is supposed to be straightforward. Okay. So what about this one? So what I want you to do now, for example, 3 is I'm going to give you, again, 2 of them. However, you'll notice here that they'll ask you to graph. Give you 2 where 1 is in standard form. Remember, this is called standard form when it's not in slope-intercept form, ax plus by equals c. And they'll give you 1 already in slope-intercept form, minus 2. So this one, I'm going to give a check mark in purple. That's done. I want everyone to put this one in slope-intercept form and tell me what happens. Intercept form. And remember, that's in y equals mx plus b. So go ahead, take a moment to do that. And then we'll discuss about it. We'll talk about it. All right. So that should be enough time. What did people get for this first equation right here that I have marked in green? Were they able to get anything?
For the first equation, I got y equals -2 plus 3 over 2x.
Negative y. Three over like this.
No negative on the y.
Oh, sorry.
That's okay.
So y equals negative 3 over 2x plus 2 or minus 2?
Mine, no, it would be y equals positive 3 over 2x minus 2.
There we go. All right, cool. So hopefully everyone did it, but if not,
Yeah, I got the same.
what do we notice? That this formula is what?
The same as the other one.
Yeah, it's the same as this. So what does that mean? They're the same graph, right? So this is an example where here's your hint here. Graphing wise, in infinitely many solutions occur when we have the same line. Now, this is interesting because I'm going to tell you right now, from my years of experience as not only a teacher, but as well as a student, right, is that no professor, no teacher, whether high school, private school, tutoring, university, is ever going to give you an equation or a problem where they say, hey, graph this, where both equations are already simplified to be the same exact thing. That's never going to happen because it's too easy. It's too apparent. So what happens is that what they will do is that they'll give you an equation where one looks like one and the other looks like something else altogether. That they will do. And then they'll go like, here are two different equations, solve, aka work with them, do what you ever need to do with them, and describe the outcome, whatever you want to call it. So that does happen. So the purpose of this is to show that, hey, sometimes simplification can yield or show the same exact line. And if it does, it has a solution of being infinitely many solutions or infinitely many answers, however you want to think of it. So what does that mean visually? Well, it's the same graph, obviously, but let me dive a little bit deeper by giving you more context in that. So let me just graph this really quick for everyone. So here's your graph. So it's a relatively easy one because I only have to graph one line basically, but I'll still do it. So -2, 2, 3, 1, 2, 3, 2, 3. So the purple one, start at -2, go up 3, 1, 2, 3, and then you move to the right twice. This way. And then the line goes up. 1, 2, 3. Huh, how funny. I graphed this incorrectly in my last class. So it's a good thing I'm doing it right here. So here's the graph in purple, which was but then if I do the same exact thing in green here, right, start at -2, go up 3, and then over. So you can see they go over each other. So what does that mean? Yeah, they're the same line, but the solution is every single x and y. So what do I mean by that? I mean that, like the previous problems, 3, 2, and 4, -1, there is a specific. So remember, backwards E means there exists. There exists a specific a specific point both lines share in common. Or an intersection, right? They intersect at a unique point, but for every upside down A, that stands for every, or for all, for every, or for all. For any xy in one graph, is the same for the other graph. So an example of that, I'll use a different color now, right? Say you plug in 1, right? X equals, or 2. X equals 2. What happens? 2, 3 halves times 2 is just 3, and 3 minus 2 is 1. What happens if you plug in a 4? Well, 3 halves times 4, 4 divided by 2 is 2, 2 times 3 is 6, 6 minus 2 is 4. So I plug in these x's and I get these y's. The same thing happens here too. But it turns out that if I plug in any x, 2, 2.5, 3, 3.5, 3.25, 3.6, pi, 100, it's always going to yield the same answer. So what that means is that it doesn't matter what point you pick for x. You can pick any point under the sun for x. It's going to give you y, and it's going to be the same for both. So that's why there's infinite many solutions. They don't cross at just one point, not 10 points, not 20 points. They cross at every single point. Well, if it's every single point in the world, then it has to be infinitely many solutions. So that's what all this was saying right here. See, so you can see here that at, what is that, 2, 1, that's a point right there. At 0, what is that, -2, they both share. And as you inch up, even if you move each x a little bit at a time, as you go in this direction, right? It doesn't matter how far into the x's you go. You can go deep into the x's in the millions, or you can go barely into the x's in this direction, -0.5, -1/2, -0.5, negative whatever. It's always going to be the same solution. That's why they describe it as infinitely many solutions, right? They share an infinite number of points together, right? Now this next example here, example 4, I'm going to show you this one instead. So this one, it's going to say graph as well. And then your two equations are 1/2 x minus 3, and then x equals -2y equals 4. So again, same vernacular here, right? This one's already in slope intercept form. And then I'll do this one really quick too. X minus, oh, sorry, that's a typo right there. don't write the double equal sign. It's just supposed to be x minus 2y equals 4. So I'll fix this one really quick. So here you can see you got to subtract x on both sides, and then this will yield a negative 2y equals negative x plus 4, and then you divide each term by negative 2, sorry. And then this gives us y equals 1/2 x minus 2. So when I have you look now, what do these guys, can you tell me about these two graphs now? So the last problem, if you will, or example, you said, oh, hey, they're the same exact thing. I mean, yeah, I mistakenly misheard one of the problems, so, I fixed whatever I was saying. Like, all right, she meant minus, she meant positive. Okay, yeah, that's my fault. That's one thing. But when you look at these two, what can you tell me about these graphs?
They have the same slope?
They do. They have the same slope. Thank you for pointing that out. Now, my follow-up question to it is from last lecture. What do we remember did we say about equations or linear equations or lines that have the same slope? Or what other property do they have? It was either last lecture or last Monday. I forgot which one it was. But I definitely said it. And if you don't remember off the top of your head, you can just flip back through your notes, right? Whatever tablet or iPad or notebook that you're writing in. You can see it because it was the, if it wasn't the last section, it was the second to last section in chapter 4.
They're parallel.
My throat's a little scratchy right now. They're parallel, right? Thank you. So here's the great thing about this. I mean, maybe a bunch of you don't think it's so great, but from a learning perspective, it's nice when you have one chapter influence the other one immediately, so you can see instant gratification in terms of your understanding that, yeah, I'm teaching you the methodology to graph, but in the whole scheme of things, you don't have to, because you already know, as long as I didn't make any typos, which I didn't, that if you recall, when two or more, remember in this class we're only going to worry about two, two or more equations have the same slope, the lines, ooh, that was messy, sorry. The lines are parallel, right? Which means your hint, graphing wise, another way to say this is no solution is an answer, or is the answer when lines are parallel, right? And why is it no solution? Remember, a solution is when they cross somewhere. So the first example, right? We're doing graphing right now, and we just talked about one solution, many solutions, and now no solution. So what happens is that from our first two examples, there is a solution. They all have solutions. It's just that they have different, they all have answers, I'm sorry, but they all have different descriptions. So for example, 1 and 2, there's a solution. There's that one single solution where they cross right there, right here. When the graphs are the same, you can see there's infinitely many solutions, right? There are multiple places. In fact, there's an infinite number of places where they both share the same solution. And again, that's obviously because they're the same line. That's the only time it will happen. But for this case, right, there is an answer, and the answer is no solution because they never cross, which parallel lines never do. So let me just draw you a little graph really quick so you can just have it for reference. So the purple one was at -3. And up 1 over 2, up 1 over 2. And the green one was at -2. And again, same thing, up 1 over 2. Oops. There we go. So as long as I don't mess up these pictures. Oh, that was bad. There's your first line. That was green. And then here I'm going to draw the same exact thing and just make sure it's parallel. Yeah, that looks pretty much parallel. Right? And then again, they never cross. The answer, again, there is an answer. The answer that there is no solution because there's no way in hell these two lines will ever cross. And that's because, again, the same slope. Yeah, the y-intercepts, they may differ. They may differ by a lot or a little bit or whatever the case might be. But the point is that they'll never cross. All right, good. So those are the 3 types that we have, right? We talked about graphing and we talked about what it looks like when you have all those possible solutions. We don't have a ton of word problems, but there definitely is one in the example, and I definitely want to, acknowledge it. All right, it came from the other lecture. Hold on, let me pull it this way. Section 305. So copy this. Copy, I'm going to paste it here in our lecture. Paste. All right, so, and then I'll erase all these things because I have to talk about this again anyway. So here is our next example, and you can see that it's a word problem, and where can I put it? Yeah, right there's fine. All right, so this is from the algebra textbook. Again, this is on page 580. And they tell you a strategy for, how to go about it. And you can follow it to a T if not. But you don't have to. It just depends on how you interpret things. And so here they tell you those steps, and then there's that. And then this is going to be our example. What is this? Example 5. Yeah, example 5 for the day. At the bottom here. Tell you that even with questions like these, they throw me for a loop every once in a while as well. All right, so what's happening here? Sandra is making 10 quarts of punch from fruit juice and club soda. The number of quarts of fruit juice is 4 times, what does that say? The number of quarts of club soda. How many quarts of fruit juice and how many quarts of club soda does Sandra need to make this punch bowl right here? Okay, so I'm gonna scroll down just so you guys can see the problems right there. So how do you tackle this, right? I mean, like I always say, right? You read it, It's, frustrating. It's not the most fun thing. And, you get over it for a brief moment and then you go, okay, cool. After that phase, how am I going to attack this? Right? What am I going to do to help myself to understand this the best I can? So what you can do is you just start with the translation like we first did within the first month or month and a half. And as you can see, there's two sets here. Notice that there are two sets of equations or two systems of linear equations, but even more practically, we are in the chapter of systems of equations. So there better be two in there some way, somehow. So what do you start with? I actually start with whatever is easiest for me. So in my case, the number of quarts of fruit juice is 4 times the number of quarts of club soda. That's what I'm going to start with. Fruit juice is 4 times the number of club soda. So when I read that, I know, let's call it juice, right? Let J equal juice. Let C equal club soda. Okay. So when I read that and I go, fruit juice is 4 times the number of club soda, well, that's easy, right? Juice, let's do lowercase j since that's what I did first. Juice is 4 times the amount of club soda. And honestly, I think that's the easier of the two to translate, right? Why? Well, you see is, and remember is means equals in terms of equations. And 4 times, right? Fruit juice is 4 times the number of whatever the other thing we're talking about, in this case, club soda. So I think that's the easier of the two. Some may agree, some may disagree, but even before knowing the solution of this problem, when I first looked at it, I was going, oh yeah, this seems the easiest to me. Okay. Now, what about the other equation that is not so obvious? I don't think it's so obvious. So it's this other one right here where she is, or he is, or whoever Sandra is making quarts of punch from fruit juice and club soda. So let me put this in a box as well. I'll use a different color here. 10 quarts of punch juice and club soda. So again, not the most obvious, but from there, based on our J and C, it's saying that J plus C equals 10. And honestly, when I say it out loud, when you're hearing it in a lecture, sure, it seems obvious. But in terms of the easiest to construct, I think that's the harder one. But again, like I said, I don't have to agree with me. It's just my observation as someone that's been doing math for a very long time. There's some things that are just easier to see and interpret really quickly, and there's some things that are not. Okay. So what do you do next? Now it just becomes like a regular graphing problem, right? You just graph and then you figure out the intersection if there is one. But in this case, there is one for sure because they're not going to give you a hypothetical where it's like, oh, just kidding. We don't need club soda or fruit juice at all. It's just a hypothetical situation. No, it's not going to do that. And in fact, none of the problems on the final are going to be like that, where they're going to have this huge psych out. Okay. But then before you graph, the question that is probably going through many people's heads, because remember, what are we trying to solve? We're trying to figure out how many quarts of each do we need, of how many of club soda and how many fruit juice. That's what we're trying to find, right? How much J, how much C, and that's what that intersection provides, right? It tells you how much. But then the question that most people are probably thinking for a brief moment is like, wait a second. What variables where in the coordinate plane. So in other words, I'm going to scroll down. If I draw you a graph, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 8, 9, 10. Yeah, there you go. Does it become C here and then J here? Or is it J here and C here? Right? You might go, what the hell? Which one do I do? Well, I'm going to tell you right now, it doesn't matter, right? Because they're both going to give you the same answer. However, what does matter is the visual representation of it. And I don't know per se if you're ever going to be in a situation where someone will direct you or be directing where they say, hey, I want you to give it to me in terms of this. I'm actually going to show you both, right? But it's something to keep in mind. So here, let me tell you this. I will say this. Traditionally, in mathematics, you go alphabetical order. ALPH, alphabetical order. So, in other words, we normally go in parentheses here. We normally go X and then Y. So if that's the case, we're going to go C and then J, and then you'll see what happens. No pun intended. So if you rewrite these equations, right, C is like X, Y plus equals 10, and then same thing here, Y equals 4X. And you don't have to do this, right? I'm just doing it for those that need to make the connection. If you understand C and J exactly as they are, perfect, no problem. So I'll do the first one with C and J because that's easy. Because that one, if you put in 0 for C, J is equal to 10. But if you put in J for 0, C equals 10. So it's basically just telling you to graph at 10 on both axes. I just want to make sure I had enough points here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yep, here we go. There's 10. And then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's 10 as well. So here is the line going down. Ooh, that's not good. Come on. There, that should be good. Right there. Okay, so this is the line J plus C equals 10. What about this one in light blue? Well, this is saying that if C is 0, J is 0. That's easy enough. But then the slope is 4 over 1, right? So you move up 4. 1, 2, 3, 4. And then you move over 1 to the right. And then you graph this. If I did this right, almost. Okay. if you look at this point right here, this one should be, I mean, I know the answer because I did it in advance, but that should be 2 comma 8. Should be a little bit, it's a little hard to see there, but there's 2 and 8 supposed to be right there. As you can see, I'm a little bit off, but again, draw as accurately as you can. Now, what does this mean? Well, remember, it's 2 comma 8, which means it's C comma J. So this translates to saying that, A, you need 2 quarts of club soda, 8 quarts of juice, fruit juice. And that's it. Right? Where they share that intersection is the answer, and you're done. But then remember, I also pose to you all, what happens if you use the reverse of this? What does it look like? Well, it actually gets inverted. Maybe not inverted, but reflected is the better word. Right? It gets reflected to look different. And let me just show you what that looks really quick. What if C and J were switched? And the moral of the story is that you'll get the same answer. It's just that your graph will look different. So say instead it was JC like this, right? So this is now your so now this is your X, and this is your Y. And I'll draw the same graph again. I mean the same coordinate plane again. Remember your equations were A plus C equals 10, and then the other one was J equals 4C. Now the good thing is that the green one will stay the same, right? You got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Since the green equation doesn't care the orientation about J being down here and C being up there, it's going to stay the same in terms of being this long triangular shape of being the hypotenuse here. Okay, so this is what I'm talking about, where you got to be a little patient with me to make sure I graph this correctly. Because it actually does matter. The accuracy matters for now. Okay. Geez, maybe I should have just left that first one. That was off only by a little bit. Nope. All right, that's the best I can do right now. Now, what about this other JC one right here? Well, that's in blue. J equals 4C. So it's opposite now, right? If J is equal to 0, then C is still 0. That's easy. But now you can see if J is equal to, say, 4, right? C is actually equal to 1. So you go 4 over 4. You go up 1, and then you draw your same line again. Of course, more accurately than me, though. There we go. That should be good right there. Perfect. So again, this is J equals 4C. and this is j plus c equals 10. So you can see the green line is the same. The blue line has been inverted or reflected. Reflected is a better word, sorry. But you can see the intersection still exists in the same place, right? So this is still 8, and this is still 2. But remember, your orientations mix now. So now you're saying that, oh, this is 8 comma 2, and you might go, well, that's not the same as 2 comma 8. But remember, the variables are also flipped too. So here, this is saying that, oh, j is equal to 8, and c is equal to 2. But then when you look at that, that's the same exact thing as this up here. See, so I know mathematically, just because of the algebra, that this question is in, as well as what we did here, because we're doing the visual graphing first, that we're going to get the same answer either way. But graphically, I know that the answers are different because it depends on the orientation of the C and J of your coordinate plane. So that's just something to keep in mind there. So you can see the green line stays the same, but the blue line gets inverted or reflected. Reflected is a better word, right? It gets reflected along the wall, this line right here, y equals x-axis. It's like a 45-degree angle. But anyway, you don't have to worry about too much of that. This is like your axes of reflection, if anyone was curious. Reflection. And it's the equation y equals x, if you ever remember that. But again, it's not necessary. All right, so what did we finish here? We have finished, this is perfect, I can write it down here in this little part. We finished graphing. And our possible solutions are what? You can have an intersection, right? That's the whole one unique solution. I'm going to abbreviate solution with SOL. You can have what the textbook calls, I'm going to put in quotation marks too, because it's just kind of weird, coincide. That's the whole infinitely many solutions. And then you can have parallel. And remember, that's known as no solution. All right. What questions do we have here, if any? All right, so this leads into our next topic, which if I scroll to the very top again, we're doing the same thing. We're still solving system of equations, but now we're doing a different method. So we did graphing, and now we're going to work on, I'll use a different color. Let's use not pink. Now we're working on substitution, right? And then I know that we're going to be able to get to hopefully all three of these, depending on how well it goes. So we're doing substitution now. Now substitution. Now again, it's the same thing, right? It depends on your methodology in terms of how you were taught this, how it was brought up, how did you go over it the first time, second time, third time, however many times you saw it. But they give you two equations, And you know what? Let me write it out this way so it's a little bit more obvious. 2x plus y equals 7. And x minus 2y equals 6. And the hint here is that you want to change an equation so that it becomes a single variable equal to something. So let me write that down really quick. Your hint here is that you want to equal to a single variable. Now you don't have to do it for both. You just want to do it for one. Which one you pick, it doesn't matter, but I'm going to demonstrate it really quick. So if you did this one on the left, right, you would essentially subtract 2x from both sides. And the equation you want to work with would be y equals negative 2x plus 7. So that's if you chose the first one. If you did the second one, you would go, oh, okay, cool. I want to add 2y to both sides. And then you would work with the equation x equals 2y plus 6. And what happens is that the whole philosophy of substitution or substituting in, what happens is that you look at both equations and you take, let's use different color. You either take this 2y plus 6 and you plug in, aka substitute, over here where this x is. Or if you take this one here, negative 2x plus 7, what y equals, right? Then what happens is that you go back to this equation and you substitute it where the y is. So this is supposed to take place where the y is. So you don't have to do both, but you definitely have to do one or the other. Probably what I end up doing is that most students, they're more drawn to the whole y equals mx plus b. So they probably will end up doing it this way. So I'm going to do it where I substitute the first equation, right? This is the first one, into your second one right here. And then I'll just follow suit here. So what do? Once you change the equation to a single variable, next you substitute in, right? Substitute to other equation and solve. So here, I'm going to color code it so it's obvious. So x minus 2y equals 6, right? You drop it down. This implies that you have x minus 2. See how this is all in black right here? Matching that of this right here. So this is the same. This is the same. The difference is taking here in light green, negative 2x plus 7, right? Because that came from here. But then still in black here equals 6. And then again, I'll underline it so that's obvious. Equals 6, equals 6. See, so those components stay the same. It's only the substitution of y that changes, right? And then at this point, it becomes just a regular solve, right? It just, let's use a different color. So you got x, and you got to distribute here, right? So negative 2 times the negative 2x becomes a positive 4x. Negative 2 times 17 becomes a negative 14 equals 6. X's combined right there. So you're left with 5x minus 14 equals 6. But then you add 14 to both sides. And then you're left with 5x equals 20. And you divide by 5 on both sides, you get x equals 4. So that is part of your answer. However, once you get your answer, that's only 1/2 of it. What do you have to do next? So substitute to the other equation and solve, and then what do you do next? Use your answer to find other variable. By plugging into either. Either is a key word there. Either original. Equation. So then what I will probably do is I would take this one, substitute it back in here. So 4 times negative 2 is 8. I'll write this out. Y equals negative 2 times 4 plus 7. So this becomes negative 8 plus 7. So y equals negative 1. Again, you'll see this one of two ways, right? You'll either see it as y equals negative 1, x equals 4, or in coordinate form, or negative 1, right? What questions there, if any? Right. This is going to be our last example right here. So what happens if you use substitution, right, and you run into a problem that looks like this? So this is our last, that was example 6. Yeah, here's example 7 now. And then they gave you these problems right here. They gave you 4x minus 3y equals 6. 15y minus 20x equals negative 30. So I think the easier one to work with is obviously the one with the smaller numbers. So you subtract 4x on both sides. That gives you negative 3y equals negative 4x plus 6, but then you have to divide everyone by a negative 3. And that implies that y is now equal to 4/3 x minus 2. So what do, right? You take this portion of the y, and you're going to substitute it back in to the second equation where that y is. And again, I'll color code it so you can see here. Remember, the 15 and the rest of this stays the same. You just got to alter 15. Here comes the 4/3 x minus 2. And then you're left with negative 20x equals negative 30. So what happens when you distribute here? Well, 15 times 4/3, that looks messy, but the nice thing is that you can divide 3 and 15, and that just becomes 5 times 4x. So that's 20x. And then what's 15 times 15 has to distribute this way, but it also has to distribute this way. What's 15 times negative 2? That's negative 30. And then you're left with negative 20x equals negative 30. Now what happens here though? Hopefully people realize that in this statement here, you see that the variables cancel. 20x cancels with negative 20x. So you're left with negative 30 is equal to negative 30. And the moral of the story is that if a little question mark here, and then you go if the variables ever cancel out correctly. Correctly is important because you don't want to just cancel randomly. You want to ask yourself, is the remaining statement true or false? So in our case, is it true that negative 30 is equal to negative 30? Boy, I hope so. This checks, so it's true. And I'm going to tell you right now, if it is true, this means the two equations are the same. So in other words, since the variables cancel out, they show that it's not dependent on the variable to find a solution, right? What this also means is that there is not a single x equals blank and y equals blank they share in common, they being the two equations. Right? There's more than one. There's multiple, if you will. That's why there's multiple solutions. That's why there's an infinite number of solutions. That's why they are the same lines, right? So the answer is that line. That's the answer, right? There isn't a single x equals whatever and y equals that they share in common. So what we have essentially done is that we've shown that substitution, we found out the unique solution, That's when we found x equals y equals. But then we also found out what it means to be infinitely many solutions as well. Now, my follow-up question is, if anybody can muster up the thinking, is that this is what happens when they're true. My follow-up question is, what if the statement was false? Right? In other words, what happens if you did the math correctly, you substituted correctly, and the variables canceled, but you didn't get negative 30 equals negative 30. You got something else. It doesn't have to be negative 30. It could be anything. But the statement is false. What if you got like 1 equals 0, or 6 equals negative 7, or 10 equals 1/2? Basically, it's an incorrect statement. It's false, right? What can you say about the lines, right? What if the statement was false? What could be said about the lines? What could be stated about the lines? Anyone have an idea? Substitution is just the algebraic form of graphing, right? We discussed graphing. We said, hey, that's one of 3 methods, and they yield 3 different solutions. When we do substitution and elimination / addition, they're just algebraic versions of the graphing. So they represent the same thing. It's just that one is visual and one's algebraic. Any ideas? And if not, that's what I want you to ponder about, because I'm going to assign homework, like I said. And what's going to happen is that come next Monday, it's not due, but get as much of it as you can done. I can show the substitution method, which we just did right now, but also the accompanying graphs that reflect this said substitution. And it doesn't have to be the same exact problem. It can be different ones as long as the results are the same, right? Where the variables cancel out and you're left with just a numerical statement, and show you what it means graphically as well as algebraically. No guesses? All right. So if there's no guesses, I'll end the recording at that so that we don't have